Hey, so this is lecture 8, part 2. We're going to cover section 5.3 on this in this part. I'm not sure if I'll get through the whole thing in this lecture. We'll give it a shot, but potentially it's a longer one. There's one really long example. Previously, we figured out how to use linear equalities, systems of linear equalities, how to put them on a graph, identify and solve for the corner points, and identify the solution regions and unbounded areas. Now in this section we're going to talk about define and evaluate linear programming terms. And then once we have some of those terms, we're going to construct a model, and then we're going to figure out how we can optimize that model from one of the graphs that we've literally just made. So we're going to cover this, this, and this. So let's get started. And I'm going to turn off my, my video feed. There we go. And these are some of the graphs we had last time. We'll leave those up. But what we're going to talk about right now are the linear programming is a mathematical process that helps with decision making. It'll use some of the graphs that we made, but it also builds on top of that. So we build a mathematical model of our problem and then use our graphical methods to find a best solution. In that, we have a lot of terms. And we'll play around with these terms a little bit. They're all defined, but then also using them will be helpful. Linear programming finds the optimal value of an objective function. And the objective function is something we're going to say regularly. And this is basically just a line. And so when we say z equals ax plus by, this is literally a line. If you were going to look at it on one of our graphs, that line is going to come in, and it's going to come in somewhere on here. And it's a thing that's going to be defined for you in the problem. You're not going to have to, you will have to figure it out, but it's going to be defined for you by the problem. Then we're going to have decision variables. Typically, the decision variables are going to be x and y. And they're going to be subject to problem constraints. And these are in the form of linear equalities. They're also going to be subject to non-negative constraints. So that's x and y are greater than or equal to 0. So we have decision variables x and y, problem constraints, which is linear inequalities, and then non-negative constraints. Points satisfying both the problem constraints and the non-negative constraints is called the feasible region. And previously when we were doing this, and I'm just pointing at the graphs now, the feasible regions were the shaded zones. So they're the zones that are shaded. Those are the feasible regions. And this is unbounded below, and this is a bounded region. This graph is upside down, but it doesn't matter for the purposes right now. And that is the feasible region. Any point in the feasible region that produces the optimal value of the objective is called the optimal solution. In a little bit it'll become clear what some of these things are, and it's not actually that hard to find some of these. The trick is working through word problems, understanding what is what. Now, there is an important thing, and that is the optimal value of the objective function. If it exists, then it occurs at one or more corner points. So if we're looking at this problem in particular, if this is our feasible region, and we have an objective function, that function is going to reach a maximum or a minimum. So it's going to reach, if the objective function is this linear value, this line, it's going to reach a maximum or a minimum at a corner point, and that, or one or more corner points. It is possible that it meets it at 2 corner points, but then that would be equivalent to this line. If the feasible region for a linear programming problem is bounded, then both a maximum and minimum exist. Always. If it's not bounded, so this problem, it's bounded, so we have both a maximum and a minimum. This problem is not bounded, so we only have a maximum or a minimum. If the feasible region is empty, then there is no maximum or minimum value. And once we're done with that, then we have to interpret the solution and what does it mean in terms of the original problem. So we have a method of constructing a model. So we introduce the decision variables. What are the decision variables? Make sure I have not a highlighter. Decision variables are x and y. X and y. and then we make a table summarizing relevant material that brings the decision variables to columns. Then we'd figure out what the objective value, what the objective is, and write a linear objective function. And then we write problem constraints using linear equations and inequalities, and we include our non-negative constraints. And then we'll use what we've just done in the last two sections, which is graph the feasible region, and to figure out what the corner points are. Once we have the corner points, we can figure out the optimal solutions. We do have an example, and I'm going to work my way through this example. So, is this large enough? I'm gonna zoom in just a little bit on this one. There, that's a little bit better. Okay. And then I'm also gonna write out right next to here. So we start out. Just give it a chance, read through it. A manufacturing plant makes two types of boats, inflatable boats. A two-person boat and a four-person boat. Each two-person boat requires 0.9 labor hours from the cutting department and 0.8 labor hours from the assembly department. Each four-person boat requires 1.8 labor hours from the cutting department and 1.2 labor hours from the assembly department. The maximum labor hours available per month in the cutting department and the assembly department is given 864 and 672 respectively. They make a profit of $25 on a two-person boat and $40 on a four-person boat. What they're asking us to do is to identify the decision variables. So what is it about this problem that we have control over? We have control over very easily two-person boats, four-person boats. So I would say X and Y. Let's identify X as a two-person boat. X is a two-person and Y is a four-person boat. So I think that's our decision variables, X and Y. And we want to summarize the relevant information. So we're going to create a table, and it's going to be something in the terms of X and Y. So a two-person and four-person boat. Looking at it, we think about what we have here, and we can just say X, Y, labor hours. So it looks like we're doing labor hours. This is a two-person boat, 0.9 and 0.8. So 0.9 and 0.8, and this is cutting. So cutting, and assembly. Okay. Now for the four-person boat, what do we have? We have 1.8 and 1.2. Okay, what else do we have? We have maximum. So we're indicated a maximum. So we have maximum labor hours available in a given month. So we have a max. Max number of hours for the cutting department is 864, and for the assembly department is 672. This is set up as a linear equation, linear inequality. So these have to be less than or equal to, And this is in terms of X and Y. Okay. So what do you think the objective function is? So what do you think it is we want to maximize or minimize? Typically, what we're going to want to maximize or minimize is cost. We're going to minimize cost. We want to maximize profit. Those are some very obvious things that we want to typically do. In this case, profit. So let's pick profit. So profit equals 25 X on each two-person boat plus 40Y. So this is our objective function. So we've now done We've identified decision variables. We summarized the information. We wrote the objective function. Write program problem constraints. So let's write problem constraints. Can we have negative boats? No, we can't have negative boats. So right off, we know that x and y have to be greater than or equal to 0. We also know that our labor hours have to be less than the maximum. So that would be 0.9 x plus 1.8 y have to be less than or equal to 864. And for assembly, we have 0.8 x plus 1.2 y are less than or equal to 672. I believe that's what we need. Then we want to graph our feasible region. So let's graph our feasible region. Sorry. Let's go ahead and do that. Let's build our little table here. X, Y, standard method. Put in a 0. Yippee. I'm going to cheat a little bit. I'm going to look forward. I didn't do it. I just created the graphs. I cheated. Okay, we'll actually do the work on this one. So what we're going to see is we're going to end up with, should I do it? I should do it. Okay. So 864 divided by 1.8 equals 480. 864 divided by 0.9 equals 960. 672 divided by 1.2, 0560. And 672 divided by 0.8, 840. So we can graph these out. Let's say 4, 9, 8. Okay. .6. Okay. So let's start about here. .6. Okay, let's go down another one here. So I'm just adjusting my scale. Sorry about that. So we have, this is my scale, and I'm doing every 2. So 1, 2, 3, 4, 480. So 480 is right about there. And 960. So 960 is right about there. We'll connect the lines. We'll draw on the axes right away. Okay, now let's see, is 0, 0 in our zone? So we have 0 is less than, so yes, 0, 0 is in our zone. And what did I do just there? So is 0 less than or equal to 864. It's true. Yes, it is. Let's graph out the next one. So you've got 0 and 560. One, two, 3, 4, 5, 50, 60, and 840. $840. $840. And then the question is 0 in our zone? 0 is less than or equal to 672 is true. So this is our region. So our region is this area. Oops. And do we have it has to be above X and Y. So we actually have a bounded region. Okay. Now, we have an objective function. Do you recall what that objective function is? The objective function is P equals 25x plus 40y. And what this objective function looks like, and is what's indicated, is it's basically a line. We want to maximize it. So it's minimized in the feasible region at this point. And as we're working up, we're going to see that these are all valid values. So we can pick anything along this line and we'll get a value of P. We reach a point here. Okay, we're still in our region. And then we come to this point. So this happens to be our maximum point. And that point is 480 by 240. It's a corner point. And this matches up with P equals 2160, I believe. So let's calculate that. So P, from what we had done earlier, is equal to 25x plus 40y using the trusty calculator. And that equals 2160. It's in dollar signs. What it tells us is that when we have 480x, so that's 480 two-person boats, and 240 four-person boats, based upon the labor we have available to us, we maximize our profit at 21,600. That's kind of a hard problem, isn't it? Well, let's talk a little bit about objective functions. So a lot of times we're going to have to figure them out from a word problem like we had to do there, or like we're going to do in this one. But before we do this, a lot of times what we're going to do is we're going to give you perhaps a graph or something of this form, right? When you're given, so if we recall this equation, these linear equalities, 3x plus y less than or equal to 21, etc., matched up with this. So let's say that our objective function was p, and p equals x plus y. And this is our objective function. We have only one corner point. So the only place that if we want to maximize it, this can only be maximized at this point. So let's try that. So if we maximize it at p, we end up with p equals 6 plus 3, which equals 9. And if we were to draw that, we would have, and x plus y is a relatively easy function. So 1, 2, 3, 4, 5, 6, maybe. That match up? Not quite. One down. Pretty close. So I drew in very lightly, and this is where our objective function would come in. So I'd probably do that in a little bit too light, but that's okay. We'll highlight it. So this is our objective function, where it crosses this line, where it intersects, and it's always at a corner point, and that maximum works out to be. So sometimes we're going to give you information like that. Now, for this one, which is this next system of equations, this is what we did the other day, or in the previous recording, where we ended up with a series of corner points. So the question is, and this is a 10. So the question is, where exactly is our maximum? So we set up what we call. So what is our objective function? What is it we think we might want to maximize? And let's say we want to maximize the function 2x plus y. So we want to both maximize and minimize it. So let's say that would be, in some cases, profit. So we want to maximize and minimize z equals 2x plus y. Okay. So in this case, we test at each point what the value is. So 2, so that would be z equals 4 plus 10 equals 14. Z equals 6. 2 times 3 is 6 plus 5 equals 11. And z equals 18 plus 3, which equals 21. And where have we maximized and minimized? So it looks like it's a minimum here, and it looks like it's a maximum here. So we have a maximum at x equals 9, y equals 3. That's this point here. And that maximum is equal to 21. And that's specifically for this objective function. So this objective function looks something like, must look something like this. So this objective function looks something like this. So it's a minimum at this point, which is just 3, 5. 3, 5. Hits a minimum here of 11, of a value of 11, and hits a maximum value of 21 when we get to here. Just recall, maximum and minimums always happen at the corner points. So I'm going to stop this video, and the next part of this will be this next example. It's a rather long example, so let's get to it.